Band subset selection and non-negative matrix factorization method for hyperspectral mixing. An RGB image is in the wavelength range 400 to 700 nanometers. A hyperspectral image is in the wavelength range 700 nanometers to 12 micrometers. Hyperspectral image bands beyond the infrared cannot be seen by the human eye, but three bands can be selected and displayed as an RGB image. Hyperspectral images have poor spatial resolution. That is, each pixel covers a square area of about 30 meters on ground. Hence, each pixel will have recorded light reflected from different materials on ground, such as water, dirt, asphalt, and/or vegetation. Hence, the pixels are called mixed pixels. The fraction of the amount of material imaged in each pixel is called spectral unmixing. Each material, such as water and vegetation, have their own spectral signature. These pure material spectra are called end-members. Equation 1, the linear mixing model, postulates the mixing of spectra imaged by the sensor as a linear model, where Y is the resulting pixel, Sk is the kth end-member out of a total of R, Ak is the abundance of the kth end-member, and W is additive noise. Additional constraints include that A is also non-negative and the sum of rows is less than or equal to 1. The way in which this algorithm is run is that you consider Y a data cloud consisting of n data points in an m-dimensional space. This dataset can be enclosed in a cone A outlined by R edges. The cone is shrunk so the edges just touch one or more points. The smallest cone that still encloses the data is likely to be unique. The edges of the cone, called extreme rays, are the basis vectors in the columns of A. For pre-processing, the independent component analysis method evaluates the weight matrix to observe how each band contributes to the ICA unmixing procedure. Then, it compares the average absolute weight coefficients of individual spectral bands and selects bands that have more information. After that, it retains most physical features of the spectral profile given only the observations of hyperspectral images. The ICA unmixing model is given by S m by p equals w m by n times x n by p, where m is the number of source signals, n is the number of observed signals, x is the observed signal, s is the source signal, and w is the weight matrix. The objective function is given by j of x, and the weight vector is decorrelated from p weight vectors using the pair of equations shown below. So this is the code that was used to implement ICA in Python using the sklearn toolbox. Hypercube decomposition is conducted by breaking image cube Y down into a product between abundance cube A and spectral matrix S. First, the error Y minus AS squared is minimized, and a multiplicative update is produced to solve the NMF problem. A is continually updated while keeping S fixed, and then S is continually updated while keeping A fixed. These updates are applied until convergence is achieved. So this method is supervised, and the numbers of n members are fixed. First, the A and S variables are initialized, and the convergence tolerance variable is defined. You have maximum iterations that are set up in the code, and a counter is started. A while loop runs the algorithm until convergence is achieved. Here's the code for loading data and entering the number of bands. Below, you can also see the original image, which is of the Jasper Ridge. It is 100 by 100 pixels and contains 198 bands. To the left, in the bottom, you can see the spectral decomposition of the ground truth image. And you also have the code for computing ICA, and the output, the user is prompted for the number of bands, and the algorithm will select the bands. Here you have the function for computing NMF, and you also have the code for calling the NMF function. And here is the output as well. You have around 59 iterations that are reached, and the lowest error achieved is about 8.57. Here are plots of the image and abundance matrices. Here you have a display of the resulting processed image, and you also have the output estimated abundance matrices juxtaposed with the ground truth abundance matrices. And you also have the functions used to display the hyperspectral image as an RGB image and to plot the abundance matrices. So summary and conclusions for this project. First of all, by unmixing, two types of information are obtained from the hyperspectral image. The first is the composition and spectral bands for each pure pixel or N member. The second is the abundances of the pure pixel for each hyperpixel. The unmixing results have been improved by implementing a pre-processing step for band subset selection using independent components analysis. This implementation uses a supervised multiplicative update method for non-negative matrix factorization where the number of N members is pre-specified. Here are my references, and thank you so much for your attention.